Okay, now we're going to switch a little bit topic, but still about some kind of memory. This is a work in progress. We've been looking at CXL memory for a while, and what we're focusing on is looking at, now that you have several levels of memory in a system, all byte addressable, how do you use them, how do you integrate them with the operating system, how does applications use that memory, and what the Computer Express Link or CXL allows you is to add essentially creating a more heterogeneous memory system where you have additional memory, still byte addressable, probably with higher latency, also maybe different bandwidth. So in a system where you want to use it efficiently, you can view it as consisting of different tiers of memory, where the application should have the most commonly used, the working set of the application, the most commonly used data should be placed in the higher tiers, and the data with lower temperatures should be placed in the lower tiers. So there's different ways you can do this. Obviously, you can just expose the different kinds of memory and put it all on the application to segregate the memory into different, or its data into the different memory locations. But ideally, you would like to just have it transparent to the application, let the system figure out what is the hot data, what is not the hot data, and then adapt the placement of data on physical memory. So if we look at a system with CXL memory, in this case we have 6 NUMA nodes. It's basically 2 processors using sub-NUMA clustering. So we have 2 NUMA nodes for 1 processor with a CXL memory attached to that processor over the PCIe lanes of that processor. So in that case, we have a couple of NUMA nodes with cores attached to them, and we have another NUMA node without any cores at all, just memory attached. Then we have an interconnect between the 2 processors and a similar configuration down here. So if we look at how normal NUMA scheduling works for Linux, the goal is to keep data close to the thread that's using it. So when you access memory, you either want to have, that is often referenced by a given thread, you want to have that memory or that data close to the thread on the same NUMA node, or so you can either move the data or you can move the thread so that they're co-located. So the way that works today is, if you use NUMA balancing, you periodically mark some of the pages inaccessible. You get a page fault. You look at whether you're on the same node as the page, and then you can migrate either the thread or the data. In certain cases where the data is shared, for example, it doesn't make sense. You can have other threads on a different node using the same data. So in that case, you need to think a little bit more about what to do. In addition to this, you only migrate the data if there's actually memory available on the given NUMA node. So once in a while, I mean, you have page reclaim running, moving data out of that NUMA node. With currently, you can enable demotion for these pages so that it will actually be moved to a slower tier, even in the NUMA balancing. So in that way, you can free up memory, and then when you do a first touch on some data, or if you touch data from another NUMA node, it will be able to be located on the same node as the thread. This is not exactly tiered. We're just moving data around between different nodes and looking at that we're accessing data in a specific place. It's not about the temperature of the data. So based on some experiments done by, let's go with the work on transparent page placement from Meta, they were looking at using instead what is the access time, when was the page last referenced, and use that to identify hot memory. So instead of using just the access and just migrating on access, you instead you mark a group of pages as inaccessible. You register when that marking was done, and then when you have a page fault, you compare to see if was this marked inaccessible recently or not, and then you migrate to a higher tier if it was recent, like within 1 second, for example. So in this case, we are promoting pages if they have been accessed recently, and again, we still need to free up memory so that we don't just fill up the higher tier. We also have to demote pages, and that works similar as before, just regular LRU page reclaim. But if you're using tiered NUMA balancing, there's a watermark that is more aggressive for when you demote stuff. So you want to have more available slots in the higher tier than with regular NUMA balancing. All right. So we're looking at this and we're trying to get a sense of how does it actually work. Is this just fine when we're using tiered memory balancing? So we're running some very simple experiments on this system that I gave an overview of before. Just to get some numbers in, we have an experimental system with CXL. It has the local DRAM latency is 115 nanoseconds. There's a penalty of about 130 nanoseconds for accessing local CXL memory, so from here to here, for example. And then if you have to go across the interconnect between the processors, there's an additional 18 nanoseconds of latency penalty. And so just a simple cache benchmark, just to get some numbers. It's using a 32 gigabyte cache, limiting the number of available DRAM in the system by just allocating kernel memory. And then see how does it work. If we look at the regular NUMA balancing, you see it's about 92 point something slowdown, 92% the performance of full DRAM. If we enable tiered NUMA balancing, we have a certain amount of promotion going on of pages, so we have about 2 million pages being promoted. Also a bunch of pages being demoted. And we see that has an effect. It's about a 2% increase in transaction rate for this simple benchmark. Still, there's a way to go if we want to. We can't really compare it to full DRAM, but there's still potentially some room for improvement, depending a little bit on the working setup of the application. Another potential way to control this is using the data access monitor. It works a little bit differently. Looking at memory still, it uses the data access bit of the page tables, and then periodically checks pages to determine the access frequency. It partitions the data into regions, and these regions it can try to adjust them maybe automatically, but within a given region, just to be able to scale, it only selects one page randomly within each measuring interval, and then sees how many hits does a given page get. So this is not particularly for a tiered memory, but just a data monitoring data monitoring tool in general. So it can track either virtual or physical addresses. And there's a recent RFC patch that proposes to integrate the hot and cold migration with the daemon, so that you can have a monitoring code that says, okay, now I identify this page as being accessed with a given frequency, and then we will migrate it as hot or as cold. And so in the RFC patch, they also have some measurements using Redis and Yahoo workloads to show that, okay, if you're looking at a mix of DRAM and the CXL attached memory, you can still go from maybe 7 to 18% slowdown to much better, to 4 or 5% slowdown. So these are already like complete software-based, well, using existing hardware features that you can use to monitor your workloads, and then try to adapt the data layout to the workload. But all the sampling isn't really perfect. First of all, the page fault based tracking that comes with a certain overhead. It also has limited capacity. I mean, you can't really mark the full memory of an application and track everything. Usually, I mean, it's like smaller chunks. The same for the data access monitor, for a daemon. You can also use performance counters like the processor event-based sampling or instruction-based sampling for Intel AMD. They also come with some problems because they're processor-centric. So they don't necessarily account for the traffic. They don't see prefetch. They don't see writebacks from cache. So you can't see all the access patterns. So with the discussions on how to use CXL and sort of the impact of having this high latency, people are starting thinking about, okay, maybe we should just add something to the memory itself so that it can tell us what data is hot and what is not. So as part of the composable memory system subgroup of the Open Compute project, there's a white paper describing a potential way to implement such a hotness tracking widget for CXL memory controllers. And basically, you'll have a hotness tracker as part of the CXL controller. You have an out-of-band or like a regular I/O-based path to configure this hotness tracker to say, okay, I'm interested in monitoring this part of the memory. And then also the device has to be able to communicate back what pages are actually hot. So in the proposal itself, it's fairly high level. I mean, it's about how is the interaction. The actual implementation details of how to do it in the device itself should be left to the hardware vendors, but I mean, there needs to be an API between the software and the hardware that makes sense. So the current proposal by CMS is that you're envisioning the monitoring happening in steps. So first you monitor at a coarse granularity. You find the regions where there's a lot of activity. Then you drill down on that particular region and do maybe a page-based or, a lower, finer-grained monitoring of that specific region. So that's the first two phases. First, locate a hot region, then locate hot pages within that region. then communicate hot pages to the host side. Software on the host side then reacts on those that information, migrates pages from the slow memory to the faster memory, and then once those pages, that information has been consumed by the host operating system, they should be deleted from the device side, saying, okay, now these pages are no longer referencing the same kind of data, so please discard that information and start tracking something else. Looking a little bit more detailed at how that would work for a memory device, like CXL, it has a decoder, but it basically operates on its own set of addresses, the device physical addresses. And so all the memory monitoring done by the memory device would be on the device physical addresses and not on the host physical addresses. The interaction with the device, most likely MMIO. The CXL has a mailbox mechanism. It's not really, for something like this, latency. It's more like you are sending a mailbox command to the device. It will respond at some point. Maybe not the best for sort of a slightly latency sensitive communication like this. If you happen to communicate at the same time, I guess as a firmware update or something. But the main thing here is that it will be based on the physical addresses of the device itself. Of course, this proposal also deals with how do you deal with the amount of information. You can adjust the sampling rate. You can adjust the granularity, both like you have small, large, and small areas that you want to monitor, but also just in general. You don't need to monitor page size. It could be something else. You can just monitor reads, writes, or both maybe. Not sure for data, hot data, whether actually tracking writes is interesting. Reads for sure are, as they're more synchronous in nature, more interesting. And so if we see how do we then, if we look at the NUMA balance, the tiered NUMA balancing that we just looked at a few slides ago, you have a flow that was based around, okay, you have a running application, you mark some of the pages, and then you get page faults. So it's all sort of a flow centered around the virtual addresses of the application and the page fault flow. But now we are having hardware that is monitoring a range of physical addresses that isn't really tied directly to a given application. The locality that you would see in an application isn't necessarily converted into locality on the device itself, because you hand out pages. So there's no reason why they should be contiguous on the device just because they are in the virtual address space. So most likely you'll need, you need something else. You need a different approach. Maybe having something more like a hotness, a service or something that can provide hotness information to the operating system, and then that can be acted upon. Of course, you could still wonder if, does it then make sense to have the NUMA balancing together with like the regular NUMA balancing, together with the hotness tracking done by hardware. And lastly, we're just looking at existing tools for daemon. It's also possible that you would, you can integrate the physical addresses into the monitoring flow, at least as part of how it's specified. it's also not necessarily given that what was proposed by CMS is actually what we want to do. Is the two-phase approach really what we want? Do you want to have more than like two phases? Do you have a lot of regions, a tree, something that continuously monitors at a coarse level and a fine-grained level, for example? You can react more quickly. And then finally, just recently, like must have been, time flies, last week, Niklas would know, but, and Damien for that matter, LSFM and BPF, there was a discussion on local memory tiering, just looking at CPU and memory decoupling maybe. So does it make sense to have both? I mean, integrated like it is today. Do people even want to have CPU? Just looking at the CPU scheduling from a NUMA perspective, as I mentioned just before, discussions about the hot memory abstraction in kernel, and also processors are not the only entity using memory anymore, so also a way to integrate with the GPUs and accelerators in general. So there was a discussion on that. Unfortunately, I wasn't able to attend, and at some point the notes for, or the agenda is linked here, and recording should become available at some point. All right, so this is all just what is going on. So what we're looking at is just see what makes sense, how do we use this in the operating system. So we're using QEMU to validate or look at the host-device interaction. Currently we have a patch set for emulating hotness tracking in a type 3 memory device, which registers with the operating system and exposes all the information with through SysFS. And then next step is to actually look at how do we do actual memory balancing with this. So also using QEMU, or just trying to figure out, I mean, is there any opportunity for improving stuff? So you can use QEMU to, or modify it to track actual access patterns to the CXL memory. Using a workload like Cache Bench again, and just seeing, is there any pages that look hot but are not promoted out of the CXL memory? And just looking at the data, there's a lot of pages not being promoted, so there should be some opportunity here. But again, well, not again, but the problem with QEMU is that the actual emulation of CXL memory is somewhat different from what a physical system would look like, since it actually emulates by trapping on each axis for the instruction. So all the caching effects are hidden. Like there's no cache on the path when you access CXL memory in QEMU. Obviously, for real CXL, caching is part of the reason for CXL, but the implementation details means that we are seeing more accesses to the memory locations that you would do on a real system. So it's not a one-to-one comparison, but currently the best that we can do. Yeah. Let me ensure I was somewhat short of one. Yeah, we have time for questions.
Do we have any questions?
One up there.
So the Linux kernel has this idle page tracking functionality. Is it used in any way to get hotness or to derive hotness out of it and migrate pages? I mean,
So-
and this one is also exposed via sysfs, from what I remember.
Yeah, so that's part of the NUMA scheduling. It's the regular, the demotion part is based on the regular LRU. I'm not sure if that's exactly the same thing or.
And idle page tracking, from what I remember, is a thing kernel says to users space that these pages have been touched recently, and you kind of are able to detect hot code pages or data pages from user space to maybe optimize the application in the end.
All right. Yeah, I don't have a clear answer to that. Then I would assume that there's some kind of connection between the two, because otherwise it seems like if you had two different subsystems, that would be kind of weird. But the exact API for that, I don't have a clear answer.
So you mentioned having these CXL hardware-based hotness counters. And I forget if you said that one of the other systems, Damon, or is there anything to monitor the hotness for DRAM in the system as it is?
Mm-hmm.
Yes. Is there any risk of requirements of standardization? What does CXL require hotness, or how does CXL define hotness? How does the DRAM-based monitoring define hotness? Is there any sort of risk in the system, or is that sort of outside the scope of what you're doing now?
Well, I would say that's probably outside, the scope in a sense, but the proposal as it is looking at a frequency-based tracking of the pages, right? So it's kind of the same type of tracking. It would only be tracking CXL memory, not the DRAM one.
So if you decided that some page is hot in CXL and it should be escalated to DRAM, how do you know what should be pulled out of DRAM?
Yeah, that's a good question. And you will still need like cold page detection on the DRAM side still. Yeah.
Okay. But that's and where is that? Is there somewhere in that interface that describes?
Not for the CXL one, and you can still, maybe you will still want to use some of the other methods for cold data detection on the host side or in the DRAM side. There's also, you can also say, well, some of those mechanisms for tracking hot and cold data from the processor side, they're not. You could also imagine, like, instead of doing something all the way on the memory, just extend the methods that are currently there on the processor side to cover all, like both DRAM and any byte addressable memory. You don't have to push it down to the memory device if you can extend the current methods to give more information. Then, there's pros and cons of that, right? Like, now you would be, would be part of imagine this would be part of the CXL standard. This is what CXL memory can tell you, and you don't have to rely on a specific processor and so on. But yeah.
Thanks. Hey, can someone help?
The device you're using, is it your own, or is it from a vendor, or is it something everyone can get their hands on, the CXL memory device?
QEMU device?
Oh, it's virtual.
Okay, so there are two different. There's a physical device that I used in the beginning. That's something you can buy, or something similar. This is like somewhat old now, so and not really a production, but it is. You can find stuff today that you can buy. You're very aggressive with your locking there. But
so if I want a CXL memory device, I can go and buy it from someone.
Yes. Don't you? Samsung makes anyway.
I wouldn't know.
Huh? Yes. Yeah.
Here,
No, Samsung, Astera, Intel, FPGA.
Yeah.
But yeah. And then both recent AMD and Intel processors also have CXL support. So so you can get systems like that. Sorry?
Not type 3, right?
No, type 3.
Type 3.
Yeah.
Only type 3.
Yeah, so I mean, for a long time you only had.
But but the standard, I mean, it's basically CXL 1.1 or something right now. So, but for this, I mean, this is for the hardware-based stuff. Of course, that's not available. I mean, it's just a proposal looked at. Maybe who knows when it's going to be, if it's going to be available, right? So, this is more about understanding. I mean, does it make sense? It's not. I'm not actually specifically promoting that this is the way to go. It's just that we want to look into it, seeing what are the issues and how do we make it part of the kernel if it becomes a thing.
Any more questions? Hands up.
We're getting ready for cinnamon buns, right?
Yeah. Everyone.
Thanks again.
Thank you.